common type of equipment that we see in industry, and we see in heating, ventilating, and air conditioning. We see in refrigeration are compressors, generally operating steady state, steady flow. And for example, in industry, we see air compressors a great deal. You've probably encountered an air compressor. Let's say when you're adding air to your car, whether you realize it or not, you're using an air compressor. Compressors for refrigerants are found in the back and bottom part of your refrigerator. Refrigerant compressors are found on heat pumps and air conditioning systems. And then, of course, air compressors all over the place. So I want to show you a couple of worked out example problems on how to analyze an air compressor. And here we go. This is a quick look at a industrial centrifugal air compressor. And so what I want to do here is cover two worked out air compressor example problems. The first will be modeling air as an ideal gas with variable specific heat. And then we'll work through the exact same problem, but treating air as an ideal gas with constant specific heat. And then we'll compare the numerical results for both. So example one, we're going to compress air at a steady rate, and we're going to model air as an ideal gas with variable specific heat. So this is what an industrial air compressor looks like. We've got ambient air coming in from the surroundings into the eye of the centrifugal compressor. So there's a shaft from that electric motor driving the compressor impeller around and around and around at very high speed. Okay, so spinning around. Okay, the compressor impeller is compressing the air to a much higher pressure, and then here's the discharge from the compressor going to an industrial process. Now, of course, I think your common sense tells you it takes power to drive an air compressor. So here's the electric motor driving that air compressor. And just sort of with me sort of eyeballing or looking at this sketch, I'm going to guess that this electric motor probably looks to me around 200, maybe up to 300 horsepower driving this large centrifugal industrial compressor. So here's going to be an example. Oh, and here's the test prep icon. This would be a right straight down the middle of the fairway test problem. So let's look at what's given and how would you attack this problem if it were a test problem. Fully insulated air compressor has inlet conditions 100 kPa and 27 degrees C. Wow, that sounds a lot like ambient air, doesn't it? And a mass flow of 1.5 kilograms per second. We want to treat the air as an ideal gas with variable specific heat. The compressor outlet pressure is 800 kPa. Changes in kinetic energy are negligible. It does say the isentropic compressor efficiency is 85%. Okay. And the assignment is determine the power required. That's one. And two, determine the exit temperature, the exit air temperature of the compressor. Now, so translation of what's given, we've got air, we've got an ideal gas with variable specific heat. That means use table A22 to get your properties. That's what that means. So we'll start with a sketch. Okay. So do you see how the sketch, we try to mimic the piece of equipment. See, this compressor is trying to depict that the flow is in here and out here, in at ambient conditions, out at a higher pressure. We're squeezing the air down. We're increasing the pressure. We're decreasing the specific volume, decreasing it. So that's why we use this sort of trapezoid. Show that. Let's see, what else have I got? Oh, notice here, I'm showing W dot out. Now, common sense says, no, that W dot is needed to run the compressor. That's why on my sketch, I show W dot of the compressor is less than 0. That's the way I depict power required by the compressor. Let's see. Our model is steady state, steady flow, open system, one inlet and one outlet. Next step, draw our process on a TS diagram. You say, well, where's the vapor dome? Where's that vapor dome? Well, the vapor dome is going to be way down here. I didn't even show it. I don't even show it on my TS diagram because we've got an ideal gas. So the ideal gas is way off to the right in terms of entropy value from the vapor dome. So that's how come we don't have the vapor dome. So what have I set up in my TS diagram sketch? Well, I draw in my initial pressure, which is a relatively low pressure, 100 kPa. There's my isobar, constant line of constant pressure. I draw in another line of constant pressure, isobar, at 800 kPa. This pressure line is more steep than this pressure line. It does turn out that you can show why this is a steeper line, but for right now, let's just remember that a higher pressure for an ideal gas represents a steeper curved up line. Okay. There's my initial state, state 1. Now, I've got a couple of states at state 2. One is if the compressor were reversible and adiabatic, it would be at state 2I, constant entropy, reversible and adiabatic. But it's not. We've got a compressor efficiency of 85%. That says that S2 actual, the actual entropy at state 2 is going to have to be to the right of 2I because, well, one is it's Q equals 0, it's insulated, so that forces the entropy to be to the right. Now, let's see, in my little yellow text box, to compare my work to the textbook work, typically the textbook calls this isentropic point 2S. In my world, I call it 2I because it's easier for me to remember 2 isentropic. And the textbook calls this simply state 2. Well, it's easier for me to remember 2 actual, 2A, 2 actual. And that's why I call it 2A instead of just 2. But you do whatever you like. But this is the way I work these problems. Okay, so this is a decent and professional looking TS diagram. Yours doesn't have to be a work of art like this, but by golly, you do need to draw it down with pencil and paper. All right, so let's move along. All right, let's think about how we'll solve the problem before we start solving the problem. The last step will be that we calculate the power. The power required to drive the compressor is going to be m dot times little w actual. And we're going to be working throughout our numerical work with little w actual and little w isentropic because it's easier. And the units of little w are going to be kilojoules per kilogram, whereas w dot is going to be kilojoules per second or kilowatts. All right. First thing we're going to do is study the isentropic turbine. Now, there is an identity for ideal gas, variable specific heat, using a variable called PR, called the relative pressure. We'll talk a little bit more about that, but it's a property that depends on the temperature of the ideal gas. But for this identity, PR2 divided by PR1 equals P2 over P1 for the isentropic process. That's what's going to enable us to find T2 isentropic. Once we get that, A22 is going to lead us to H2 isentropic. So once we get H2 isentropic, we will then determine the isentropic work, little w sub I, using the first law. Then we'll apply the compressor efficiency to find W actual. That's going to be easy. Then, once we've got W actual, we'll multiply by the mass flow rate to get W dot actual. And one thing I forgot to mention on our approach is then we've got to go back and use the first law once we have W actual to back calculate T2 actual. And that'll be easy. All right, so let's plan ahead before we start crunching numbers. We're going to need H1. All right, we'll get that from table A22, as well as PR1 at T1. That's going to enable us to find PR2. Now, once we have PR2, then we're going to go into table A22 to back calculate T2 isentropic. Once we have that, we will calculate H2 isentropic. Then we'll use the first law to determine the isentropic work, and then use the first law to get the, and then we'll apply turbine efficiency to get the actual work. Okay, so let's go to our table A22 to write down H1 and PR1. Okay, so let's see, H1 is easy. We write down 300.19 at a 300 degrees K inlet. Okay, let's see. Look at these columns. Delta S equals 0. In other words, these two columns, whatever they are, they only apply to isentropic processes for air. Delta S equals 0, isentropic only. Okay. So with that little special case, we're going to write down PR1 as 1.386, PR1. Okay, we write it down. The next thing we do is we go back to this identity. It says for isentropic processes, for ideal gas, constant specific, variable specific heat, P2 over P1 equals PR2 over PR1. And boy, I've written that out. So you could think of this as a formula. If it's on your formula sheet, you've got to have next to it isentropic process only. Okay. And this would be relative. These are what's called relative pressures. Okay. So this enables us to solve for the relative pressure at P2, PR2 equals PR1, P2 over P1. So let's do the math. PR1 we wrote down from before. We just wrote that down. So PR2 is going to be 8 times PR1, or 11.088. So now we're going to go back to table A2 to figure out H2I and T2I now that we know PR2 is 11.088. All right, we're going to go all the way over to the right-hand side of this table A22. Where were we to start with? Here we were over here to start with. Now the temperature is getting hotter, so we've got to come way over to the right-hand side and look for the number 11.088. I don't see it exactly, but it's close to 11.1. So it's in between 530 and 540. It's in between these two enthalpy values. So we will interpolate. We'll set up a little interpolation table. Okay, here's my number, 11.088. We've got to determine these two numbers in the white cells. We'll just do a straight interpolation to determine that T2I is 539.8 and H2I is 544.18. Makes sense, doesn't it? Because notice how close, we're damn close to 11.1, all right? But just for completeness, we went ahead and interpolated. Look how close we are to this value, 540. And we're very close numerically to 544.35. But the interpolation is the right thing to do. All right, we'll move on. Okay, so now we have H2I, so we can solve for W isentropic using the first law. Okay, this isn't a formula. This is the first law. Qn, that's 0, minus W isentropic equals H2I minus H1. Well, do you see, I've got a minus sign over here, so I flipped it. I didn't show all of the laborious work, but it makes sense. I think you can see with your eyes, W isentropic in the first law, H1 minus H2I. Got it. So here's W isentropic. It's negative 243.99 kilojoules per kilogram. Does that make sense? I've got a negative number. Does that make sense? Yes, I'm running an air compressor. It takes power. It takes work to increase the pressure of the air. It makes sense that WI is a negative number. Okay, now let's work on compressor efficiency. You shouldn't have to go to a formula sheet or even the textbook to figure out the definition of compressor efficiency. Figure it out on your own. Compressor efficiency is always less than or equal to 100%. Now, think in your mind. If I've got an air compressor that's reversible and adiabatic, would that take more or less power than if the compressor were adiabatic and irreversible? Or not, let's flip it. Which would take more power to drive a compressor? One that is adiabatic and irreversible, or one that is adiabatic and reversible? Common sense says it would take less power for the reversible and adiabatic, less power. So you got more power in the denominator, less power in the numerator. You can figure out compressor efficiency is W isentropic over W actual. You can do that when it's high stress, when you're taking a test or a quiz. You figure it out. It will take 10 seconds, 5 seconds to figure that out. It'll take less time to figure it out than to go to a formula sheet. All right, so W actual is W isentropic divided by the compressor efficiency. And so we'll do the math. Negative 243.99 W isentropic divided by 0.85 gives a bigger negative number. W actual is negative 287.05 kilojoules per kilogram. So now we'll apply the mass flow rate to get the power. Multiply by 1.5 to get negative 430.6 kilowatts. Negative. So the power required. So here on my test, I'm going to write out in a sentence, the air compressor requires 431 kilowatts of power. Boom, done. No, whoops, we've got to get T2 actual. So we're almost there. We'll apply the first law, steady state, steady flow for the actual adiabatic process, Q is 0. So W actual is H1 minus H2A. Okay. H2A is, so I'm going to solve for H2 actual, H1 minus W actual. I've got both numbers on the right-hand side. So H2A is 587.24. Okay, well, back to table A22, 587.24. It's in between 580 and 590. I'm going to have to interpolate again. And I do the interpolation, 581.1 degrees K, subtract 273. So the air compressor outlet temperature is 308 degrees C. That's hot. That is really hot. And so that's why it's important to calculate this T2 actual, because in the real world, if this is an industrial air compressor, we're going to have to add another piece of equipment downstream of that air compressor to cool down that hot air for us to be useful, right? So we want to be able to touch the pipe that's conveying the compressed air. So we've got to have compressed air that's like up maybe 40 degrees C or 50 degrees C would be the absolute hottest we could sustain it. So we'll need to add a heat exchanger that's called an after cooler to this for a true industrial installation of an air compressor. Okay, let's do exactly the same problem, but with a different ideal gas model. We're going to model ideal gas as having constant specific heat. We'll go through the numerics and compare the results. Okay, exact same test problem. Now, we've got the test prep icon there. If I were your instructor, this would be the test problem you would get from me, because most of my practice in engineering, when I was dealing with compressed air problems, I was treating air as an ideal gas with constant specific heat. And generally, I was getting great results, nearly always. Getting great results treating air as an ideal gas with constant specific heat. So exactly the same problem statement. Okay. What does this translation mean? Now, for constant specific heat, when we need to calculate enthalpy changes, H2 minus H1, we simply use Cp times T2 minus T1. Easy. Cp is a constant number. When we want to study an isentropic process for an ideal gas with constant specific heat, we use the identity PV to the K is constant. We should know this in our heads, but we should also know the restrictions. PV to the K is constant. Isentropic process, that's reversible adiabatic. Ideal gas, constant specific heat. And for air, K is always Cp over Cv, but for air, K is equal to 1.4. We should have that in our heads. As we gain experience in air compressor analysis, we just learned that K is 1.4 for air. Okay, the sketch, exactly the same. Air compressor, exactly the same. TS diagram, exactly the same. Okay. So now here's our solution approach, slightly different. Now, the last step, exactly the same. We're going to find W actual in our work, but then we're going to multiply it by M dot to get W dot. W actual, kilojoules per kilogram, times M dot, kilograms per second, is going to equal to kilojoules per second or kilowatts. Same approach. Now, isentropic compressor, ideal gas constant specific heat, P1V1 to the K equals P2V2 to the K. We're going to be able to derive, we're going to need an expression for T2I equals. I'm going to show you how to do that. You should be able to do this derivation without going to a formula sheet. We'll go that in a second. Next, we're going to use the first law to determine the isentropic work, little wi. We will apply the compressor efficiency definition to get to W actual, okay? And then we'll multiply W actual by M dot to get to W dot actual. I forgot to put on here, then we'll use the first law to back calculate T2 actual coming out, T2A. So let's plan ahead. We need K and we need C sub P for air. Let's use the inlet condition. Here we go. We're going to go to A20. We're going to find air. We're going to write down C sub P at the inlet condition is 1.005 kilojoules per kilogram degree K, and K is 1.4 if you don't remember it. Now we're going to study the isentropic compressor, Okay, 1 to 2I. P1V1 of the K is P2V2 of the K, but what we're seeking to find is T2I. I don't see that in my formula. Wow. Let's remember the ideal gas equation of state. V is RT over P, or PV is equal to RT, or V is little v. Okay. Well, let's substitute into our governing equation. PV of the K is constant. Now, I'm not going to drag you through all of these algebra steps, but you might want to download the PowerPoint slides that go with this video so you can satisfy yourself that you can quickly get to this identity. T2 isentropic equals T1 times the pressure ratio, P2 over P1, to the K minus 1 over K. You should be able to get to that without depending on a formula sheet for this formula. If you put this on your formula sheet, you've got to add some words to it. That is isentropic process, ideal gas, constant specific heat. Okay. All right, well, let's do the math. I'm going to write P2 and P1 are given. T1 given 300. K minus 1 over K is 0.286. Just do the algebra. Okay. Then do the algebra here with the calculator. T2I, plug and chug, 543.4 degrees K is T2 isentropic. Boom. All right, now we've got T2 isentropic. We're going to use the first law to solve for W isentropic. It's just H1 minus H2I. Do you see how I said that? Well, I wrote down the first law. Q in, that's 0, minus W out equals H2I minus H1. Well, how do I get the, oh, I see. I've got a minus sign over here. And so visually did that. I didn't drag you through all the steps to get to this. You should be able to see catch on to this pretty quickly now. Now, H2 minus H1 minus H2. Ideal gas constant specific heat. That's just going to be CP times T1 minus T2I. Great. We've got all of these on the right-hand side. So W isentropic is negative 244.65. Does that make sense? Yes, it does. Yeah, negative number. We're compressing air. Makes sense. Definition of compressor efficiency, which is going to take less power to drive a compressor, an isentropic compressor or an actual compressor. It's going to take the least amount of power needed will be the isentropic case. Makes sense. So W actual is W isentropic over turbine. Look at that. Look at that. That's the old copy and paste problem. That should be compressor efficiency. I need to make another 21. Slide 21, I've got to fix. That's compressor efficiency over there. Sorry about that. At least I got it right in my solution. WI, negative 244.65, 85% efficiency. So W actual is a bigger negative number, negative 287.83. W dot actual is M dot times little w actual, negative 431.7. So on my test problem, I'm going to write out the air compressor requires 432 kilowatts of power. Find T2A. Very easy again, now that we've got ideal gas with constant specific heat. W actual is H1 minus H2 actual. That's CP times T2 minus T1 actual. We're going to back solve for T2A. W actual we just found. And so T2 actual is 313. I'm sorry. T2 actual is 586.39 degrees K. Subtract 270 to get 313 degrees C. So I'll write out on my test, the air compressor outlet temperature is 313 degrees C. All right, let's recap and compare. Let's compare both approaches to solving the same problem. All right, same problem. Ideal gas with variable specific heat, power needed 431. Ideal gas constant specific heat, 432. Wow. Well, when you do these problems, it's more than homework. It's basically you're trying to determine the electric motor size needed to drive the compressor. That's the real world application. So, electric motors don't, there's not that much precision in electric motors. You're either buying a 200 or a 300 or a 400 or a 500 horsepower motor. So your conclusion is easy. You had better purchase a 500 horsepower motor for this application. On the outlet temperature, 308 using variable specific heat, 313 using constant specific heat. Are they different? Yeah, but not by much. What's the practical application? You're going to be needing to size out an aftercooler, a heat exchanger. You see that practically, look, your heat exchanger sizing, your heat exchanger design is going to be pretty much exactly the same. And so which approach is correct? Both are correct. So there's not an exact right for this type of industrial situation. There's not the approach. Both will work for you. Okay. So let's see, a final recap. In our compressor analysis, what we do is we study the isentropic process first. We then apply the definition of turbine. I've got to fix that. Slide 25 is all goofed up. Apply compressor efficiency. Apply compressor. That darn copy and paste does not fix my errors. All right. And then apply compressor efficiency. And then finally determine the actual process results using the first law for steady state, steady flow open systems. Okay, well, shame on me for not checking my PowerPoint close enough, but I think you get the idea, right? And so that is some worked out examples for how you would analyze real honest to goodness air compressor problems.